Hello everybody, how are you? Hope all of you are doing well. Welcome to our channel Turbo Electronics Education. After a long time though we are meeting. So today's session is very much interesting and as well as very much important also, because in today's video we are going to discuss about delta modulation and adaptive delta modulation just for our lab purpose. Okay, so see, the delta modulation, adaptive delta modulation, these topics are very vast topics, and theoretically if you study these topics it will take, for each and every topic, each of these topics may take 1.5 hours. So I am just going to cover three topics, three topics, that is delta modulation, adaptive delta modulation as well as sigma modulation, just for our lab purpose. Just like as previous video, I am not going into detailed analysis of these types of modulation techniques, and I am not going to show you the disgusting equations also. Just a small overview just for understanding the laboratory purpose. Okay, so I am going to cover three such like topics. So this video may be little more lengthy also, so don't worry about it. And I will request all of you to watch this video from starting to end. It will be more helpful to you and you will understand each and every points about delta modulation, what is happening, why it is happening, and why delta modulation is disadvantageous, etc, etc. So let us first see our topics, our outcomes that we are going to discuss. These are our course outcomes that we are going to discuss in today's video. So first of all we will see sampling a signal. See, in our last video, as far as I can remember, that I have already told you about the sampling and how sampling can be done, what are the three types of sampling, which sampling is the best sampling that we have chosen so far. And so in today's video I am not going to details about the sampling and the Nyquist sampling theorem. I am just going to give you a brief overview about the observational story. Where if you sample a sinusoid, that is a sinusoidal signal or cosinusoidal signal, if you sample the sinusoidal or cosinusoidal signal using an impulse sampling, though impulse is not possible physically, if you sample these small width impulses, small width pulses, okay, then what are the waveforms, how the waveforms are coming out, and what will be the sampled signal, how the sampled signal of a sinusoid will looks like. I am just going to discuss this thing in this video. Okay, then we will see our main topic we will enter, that is the delta modulation. This topic is very important. Okay, I'm just marking it right now over here. Why this is interesting and important also, because the techniques of delta modulation, adaptive delta modulation and sigma modulation techniques are same. So each of this modulation has covered the demerits of its previous ones actually. So after studying the delta modulation, the general question that came in our mind, that delta modulation had some problems, some demerits also. We will see the demerits in this video, and we will also see how adaptive delta modulation recovers those demerits, and how the delta modulation has become more advantageous, more disadvantageous, and adaptive delta modulation has become more advantageous. And we will see how the problem has been recovered, and then after we will see the sigma delta modulation. And sigma delta modulation has two parts actually, one is first order and one is second order. So for sigma delta modulation I am not going to show you the detailed waveforms as well as the operation, because sigma delta modulation is not in our theoretical syllabus. So that's where I am just going to show you about the diagrammatic study. I'm just going to show you, and I'm just going to differentiate what is the first order, what is the second order sigma delta modulation, and how the modulating diagram, how the transmitting end diagram looks like. and later then we will see the demodulation technique. See, the demodulation techniques for delta modulation, adaptive delta modulation as well as the sigma delta modulation is same. Just a single integrator has been used at the demodulator circuitry. Why this single integrator has been used, I will tell you, and I will prove that in using integrator we are getting, mathematically we will get this same sinusoidal signal that we have transmitted. Okay. And one more interesting thing that the most of the people may confuse, that is this all types of modulation techniques that I am going to discuss over here, three modulation techniques. All these three modulation techniques are digital modulation techniques. Digital modulation technique means I will give it a sinusoidal or message signal that is analogous from, and it will generate the digital bits, digital signals, that is in the forms of zeros and ones. Okay, so that's why it is called the digital modulation technique. The input is a sinusoidal or the voice signal or the message signal. There is a time domain random or deterministic signal, it may be. The output will be in the form of digital pulses or digital codes. So that's why it is called the digital modulation techniques. And in case of demodulation, you can easily understand that we will input the digital pulses or digital codes, and it will generate the original our message signal that will be continuous in time domain. Okay, so these are the course outcomes that we are going to discuss in details in today's video. So without wasting any more time, let's start our video. See, our first topic is sampling a signal. For sampling a signal, see, let us assume that the sinusoidal is a signal. Okay, if we sample this sinusoidal signal into impulses, using impulses, then what will be the output? I am considering that these are the unit impulses, so the output will be like this. Right, this will be the output, and I have discussed it in the sampling theorem in the sampling video, where I have discussed the sampling. That is, we cannot generate this impulse signal physically. As we cannot generate this impulse signal physically, the sampling that we are getting mathematically here, we cannot see it physically. So what we can generate in place of this impulse signal, we can generate the small number of pulses. Okay, we can generate the pulses of small widths. Okay, these are the pulses of small width. Now if I multiply this signal with these pulses, then the waveform will looks like this. Okay, the signal will looks like this. Now here a sample and hold circuit that is used. Sample plus hold, this circuit is used. And how this sample and hold circuit performing sampling over here, that we will see. Let us consider a large waveform for better understanding. Let me draw this waveform first. assume that this is a signal. Okay, and just for simplicity I am assuming here we are multiplying this signal with an impulse train. Okay, though the impulse train is not possible to make in real worlds, but we are assuming that we are just multiplying this with impulse trains. And physically what is possible, actually physically generation of pulses of small width is possible, just like it. You cannot generate it, but for assumption, for calculation, for better approximation, for understanding purpose only, we are taking this impulse trains. So I am also assuming that the magnitude of the impulse train is 1 here. If the magnitude of the impulse train is 1 here, that's why when the impulse train will be multiplied with this signal, the discretized or the discrete sinusoidal signal that will be generated after this will be in that magnitude that it was in its previous form. That means the no amplification will be done over here, because the magnitudes, each of the magnitudes of the sampling instances of a particular sampling instances, each of the magnitudes are being multiplied with this one. That's why the magnitudes of the discrete sinusoidal signal will remain same. No amplification will be done. So let us see what is happening over here. See, there is a particular time interval in between two samples, and that time interval is called the TS. That is the sampling time. Sampling time is nothing but the time interval between two instantaneous pulses, that may be impulse or square pulse of small width also. So that's not the big discussion. What is the pulses, what are the pulses, what is the type of pulses that we are going to take for sampling. Our main motto is just to understand that there is a particular time interval in between two samples. Suppose in this interval, first interval, I am assuming this is a first sampling time, that is the 0th sampling time I am assuming. First sampling, after the first sampling, it has denoted the magnitude of this sinusoidal signal at t equal to 0th position. This is the 0th position. This is 1 position, this is 2 second position, 3rd position, 4th position, 5th position, 6th position, 7th, 8th, 9th, 10th, 11. I am assuming. Okay, this is also 0, 1, 2, 3, 4, 5, 7, 8, 9, 10, 11. Now, suppose at t is equal to 0, the first sample has been taken over here. After as the amplitude of this sample is 1, that's why at t is equal to 0, the sample that it has taken, that means at t is equal to 0, the value of the sinusoidal signal has been multiplied with this impulse train, that is the first impulse, and it has denoted the magnitude of the sinusoidal is here. As the name suggests, sample and hold, that after the first sampling it will hold this value what it has sampled. Up to what time it will hold this value? Up to the next sample. That means after the first sample it will hold its value up till the next sample. Okay, after the first sample it will hold its value till the next sample has been taken. When the next sample will occur over here, it will again test its value, that is this. At first t is equal to 0, this sampling value, this sampled magnitude has been taken, and at t is equal to 1, this sample magnitude has been taken. In between these two sampling instances, the value of the previous sample will be held by the sample and hold circuit until the second sample, the next sample has been taken. Again, after first sampling, that t is equal to 1, sampling after sampling at t is equal to 1, this sample has been taken and this value will be hold until the next sample has been taken. Again, at t is equal to 2, is this sample has been taken, this value will be hold until the third t is equal to 3 sample has been taken. At t is equal to 3, this sample has been taken, the value will be hold until the next sample has been taken. When next sample is taken, the value will be this, and in this way the value, there is a signal will be discretized, okay, or you may also call it the signal has been sampled. The black signal that I have shown over here, that is the sampled signal, okay. As the sampling and hold circuit is working here, that's why the sampled value of each and every point or each and every sampling instances has been hold until the next sample has been taken. That's why there is a flat response has been produced in between two sampling instances. This is the main funda over here. If we don't provide the sample and hold circuit, then what the output waveform will be? Only the magnitudes. That means like this, only the magnitudes. The output waveform will be only the magnitudes, okay. As the sample and hold circuit is provided over here, that's why it is holding the value of the sample until the next sample has been taken. So this waveform that has been produced over here, this is called, this black waveform is called sample signal, okay. This is called the sample signal, and this is called the time domain signal or the main signal. This time domain signal has been sampled and hold using the sample and hold circuit, and this has been generated like this, okay. This is the basic funda about what happens when we sample a sinusoidal signal. And for more better understanding, I am giving you a mathematics, that is, suppose let us assume the signal is a sin omega t, okay, and I am multiplying this signal with an instant, with an sampling, with the impulse train actually. That is, suppose the impulse train means dn, okay. Now what will happen over here? The impulse train is nothing but delta of n plus delta of n minus 1 plus delta of n minus 2 plus delta of n minus 3, and like this. Now this a sin omega t will be multiplied with each of this delta, that is a sin omega t into delta n plus a sin omega t into delta n minus 1 plus like this. Now we know a property of this delta function, that is, when the delta function, when a delta signal or the impulse signal is multiplied over a signal, that gives that value of this signal of that where the impulse is present actually. Suppose this impulse is present at t is equal to 0. When this impulse will be multiplied with this signal, then the value of the signal at t is equal to 0 will be the output, that is a sin omega t at t is equal to 0 will be the output over here, plus a sin omega t at t is equal to 1 will be output over here, and in this way it will continue. That means you are getting this signal for number of times but for different time intervals. That means for t is equal to 0 you are getting this same signal, for t is equal to 1 you are getting this same signal again and again, but just in different amplitudes. Why in different amplitudes? Because at each and every time the amplitude is continuously changing, that's why it is continuous time signal, right? So the amplitude is changing of the sinusoid, okay? So that's why at each and every time instances, for different time you will get some different amplitudes. The whole circuit, this is the sampling circuit is doing here. Actually the whole circuit is just holding the amplitudes, there's nothing more about it. Now let us see what is the delta modulation. Now we have, as far as we have studied, we have just generated a sample signal from a sinusoidal signal or any kind of time domain continuous time signal, okay? So now what we are going to do, we are going to generate this sample signal, that is our part 2. Part 2 is the delta modulation, that is DM. We are going to generate digital pulses from the sample signal, digital pulses. Now our motto is just to generate the sample signal. Actually this is a sample signal, okay? That means we are going to write t is equal to nts. So as this is a sample signal, that's why we have written t is equal to nts. From this sample signal we are going to generate the digital pulses or the datas, digital datas, that is in the form of zeros and ones, okay? Now how we can generate this digital data, okay? Let us see that. Suppose this is a continuous time signal that I am going to draw over here. This is a continuous time signal. Now for delta modulation, two things that you must have assumed, that is the sampling time instant, is the TS is constant. That means we cannot change the value of the TS. The sampling time instance, the sampling time interval is constant for delta modulation, and the step size is also constant. Now what is the step size? I will show you, don't worry about it, but just for now remember the step size and the sampling time instant for delta modulation is constant. Now what is the corresponding discrete signal or the corresponding sample signal is generating? That is like this. It is something like this. Let me draw it. This is the corresponding signal that is generating over here, and this is called the step, a single step or step size, that is denoted by delta. This is called, actually, this is the step size, and this step size is constant, and this is the sampling interval, that is the TS, sampling interval. This is also constant. Now what is now happening? So according to this signal, according to this continuous time signal, we are generating a sampled signal, but that sampled signal must have same sampling time interval as well as the constant step size. Whatever we have seen in the previous session, according to the continuous time signal, we are just considering a fixed sampling instances, that is the TS was fixed, but the step size was not fixed over there. So I will discuss this later, why the step size is not fixed over there and what is the disadvantage that is providing a fixed step size over here. That is, I have already told you that delta modulation have some disadvantages, we will see it later. But just for now you are considering that a fixed step size as well as the fixed time interval is going to provide it. That is, the sampling, during sampling the TS is also constant and step size is also constant. So that's what I have written over here, that is the step size is also constant. According to the signal variation, the step size is increasing, and after a certain time the step size is decreasing, and then again it is increasing, something like this. Okay. Now as the step size is constant, first of all I will discuss how the codes are generating. This is the signal that has been generated inside it. Now how the codes has been generated. Now codes has been generated, that is very easy. What is happening over here? Let us see. For first interval, I am assuming the first code is 1. When it will sample the next interval, when it will check the next sample, then it will continuously compare the present sample with the last sample. That means when the next sample will be taken, that is the next sample will be taken, it will compare whether the last sample was greater than from the present sample or not. Suppose S1T is the present sample, and S2T is the next sample. Next sample, that means we are standing at S2T. After standing on S2T, if we see that the S2T is greater than S1T, then we will take a 1. If the vice versa happens, that is S2T less than S1T, then it will take a 0. Obviously you must have remembered that here T equal to NTS. That means it is not a continuous time signal over here. We are taking the samples, that's why T is equal to NTS, and this TS is fixed and N is the number of samples, that is the TS, 2TS, 3TS. N is equal to 0 to infinity. Okay, TS, 2TS, 3TS, in this way we are taking these samples. So we must have to consider this thing for delta modulation. Not only in delta modulation, for adaptive delta modulation we will also consider this thing. So now in this way, whenever the present sample value will be greater than the previous ones, this will generate 1. That means here 1 will generate, here also 1 will generate 1, and when the present sample value is less than, you can see that this sample value is less than the previous sample, okay, then a 0 will produce. Okay, again when the present sample value will be less than, this sample value is less than, this sample value is less than, actually this sample value is below this, so that's why we are saying that this sample value is less than this, and then at that time again a 0 will produce. In this way it will continue producing 0 unless or until it will find that the previous sample value is greater than this. Now at this point it is saying, it is just saying that the present, this sample value is greater than this sample value is greater than this. At that time it will generate again 1, and at this instant it is also saying that this sample value is greater than this, it is again 1 here, and at this instant it is saying that this sample value is greater than the previous one, and this stage it is again 1. So in this stage, this is the bit stream that we have got over here. This is the delta modulated stream. Okay, this is nothing but that delta modulated stream. Okay, so whatever we are going to see here, that is after a particular constant time interval, that is Ts, it is watching whether the value of the particular time, that is for t is equal to 0, suppose it is sampling here, for t is equal to 1 it is sampling here. If it sees that the particular time, that means the at that particular time, if it sees, if it notices that the amplitude that it is sampled is greater than the previous sampled amplitude, the amplitude at present that whatever it has sampled is greater than the last sample amplitude, then at that time it will produce a single 1 here. Again for next sample it is seeing that the amplitude of this time is greater than this, then it will produce a 1. Okay, and whenever it will produce a 1, the simple thing, that is whenever it will produce a 1, a pulse step will be uprising, and whenever it will start producing 0, the pulses will be downwards. Okay, when it will see a 0, then the pulses will be downwards. Okay, so that's what actually the delta modulation doing over here. So now don't think about these impulses are the sample signal of this. Here the signal that has been produced, that has been written in blue line, that is blue colored signal, looks like a PAM signal though. So this is not as well as the PAM signal, and this is not also the sample signal of this black signal. Okay, what is this signal? This signal is nothing but the representation of this code. Okay, what is actually doing, what's the circuit is actually doing? The circuit is doing, at first instant suppose it is assuming that it is 1. Now at second instant it is checking the amplitude of this black signal. If the amplitude of this black signal is greater than the previous amplitude, then it is producing 1, and when this 1 is produced, a uprising step is produced over here. Okay, whenever again the 1 is produced, a step is produced. That's why the step size is constant. If we draw this step size, that is whenever a 1 is produced, a particular fixed step is produced, again a particular fixed step is produced, particular fixed step is produced if the 1 is producing. When the zeros are producing, that's one, what is happening, a downward step is produced, again a down step is produced, again a down step is produced. That means the zeros are producing. These steps that you can see, the blue colored line, that is generating due to this. Actually the reverse is generating. Whenever this it is saying that the present sample amplitude is greater than the last sample amplitude. So whenever it is seeing the present sample amplitude is greater than the last sample amplitude, one upsteps is producing, and at that time simultaneously a 1 is producing. Again it is saying that the present sample amplitude is greater than the last sample amplitude. This sample amplitude, see, this sample amplitude is greater than last sample amplitude. At that time a upstep is producing as well as a 1 is producing, and in this way it is proceeding. Again at this time, at this sampling time, actually at this sampling time, it is saying that this amplitude is greater than the last amplitude. Upstep is producing as well as a 1 is producing. In this way it is proceeding actually. And this waveform that you are seeing over here, this is the DM output, and according to this DM output, this bit stream are going to be produced. Okay, this is the delta modulation. With this I have covered the second topic also. Now the third topic is, what are the disadvantages of delta modulation? See, I have also already considered the delta modulation has the two things. That is what? It has the constant sampling time as well as the constant step size. This is the step size and this is the sampling time. So what is the problem with this delta modulation is, there are two problems. That is the problems. First problem is slope overload problem. What is the slope overload? Slope overload is, suppose the input signal is drastically varying, or the frequency of the input signal is very much greater. As the step size of this signal, of this delta modulation is fixed, that's why it cannot follow the drastic change or the drastic slope of the input signal. The delta modulated waveform, that is the DM output waveform, what will be the waveform will be produced at t is equal to 0. It is saying that the amplitude is, it is assuming the amplitude is 0. So this is produced. After a particular sampling time, it is saying that the amplitude is greater than the previous one. This is produce a fixed step size. After a particular time interval, it is saying the amplitude is greater than the previous one. It is producing a fixed step size. Okay. Again, after a particular time, it is saying the amplitude is less than the previous one. That's why it is producing a down step. In this way, it is again producing a down step. And after this, after a particular TS time, it is seeing the amplitude is the previous lesser than the previous one. It is again producing the down step. In this way, it is producing this DM output waveform. Okay. Now you can see that the output waveform that has been produced over here is not too much matched with the black line output waveform, black line input waveform. Actually the black line that has been shown over here, that is the input signal or the voice signal, and the blue color line is the DM output waveform. You can see that the output waveform is not too much matched with the input waveform, and if you see the slope of these two waveforms, then you will see that the slope of this waveform is less than the original slope. That means the original slope is greater than the DM output waveform slope. Okay, the original signal slope, that is the initial slope what the signal had, is greater than the output slope of this DM. Okay, that the delta modulated output waveform slope is less than the input signal slope. So that's why we can tell that the input signal slope is overloaded. This is the greater than the output slope, means the input signal slope is overloaded on the delta modulation DM output signal slope. Okay, why it is overloaded? That means the signal slope is too high that the delta modulation cannot follow this slope exactly. And you will understand it better if the signal is that the signal has the less slope. How? If the signal has the less slope, then you can see that the delta modulation very easily can follow this signal, though it has the fixed step size as well as the fixed sampling time interval. That means the step size is actually fixed, and this sampling time interval, that is the TS, this is also fixed. Here these are also fixed also. The delta is also fixed. The sampling time interval, which is the TS, is also fixed. So you can see that for low frequency signal, or you can say that the signal that has the less slope, less initial slope, that means the signal is not varying too much with respect to time, then the DM output waveform that is producing over here is much more close to the actually the original signal is. That means you can see that the both of the waveforms are almost overlapped. That means we can also tell that the discrete waveform that the DM has produced, we can easily extract from this discrete waveform to the original waveform, as the discrete waveform has almost followed up the input signal waveform. In this case, as the signal is varying very much, that means is at the initial slope of the signal, that is the black colored denoted over here. So the black colored signal, or the initial input signal, has the much more slope than the delta modulated signal waveform. That's why the slope of the initial or the input signal has been overloaded on the DM output signal. Okay, so this is the problem of this delta modulation. That means we have understood that for delta modulation, the drastically varying signal cannot produce the appropriate digital data or the appropriate delta modulation output signal. Okay, this is the first problem. Now there is a second problem, that is the granular noise. That is the granular noise. What is the second problem telling? Second problem is, suppose, assume that a signal is like this. That means after a particular time the signal is not varying too much, or the signal has become almost constant. Okay, at that time what the delta modulation output will be? The delta modulation, what will do? It has again the fixed step size as well as the fixed sampling time interval. That's why after a particular sampling, after a particular time, it is just going to see the present sample value or the present amplitude with the past amplitude. After comparing the present amplitude or the present sample amplitude with the past sample amplitude, it is taking its decision whether the output will be 0 or 1. That means I am again drawing the delta modulated waveform over here. That is, suppose the first sample has been taken here, the second sample has been taken here. Remember that always whenever you will try to draw the DM output waveform, you must have to remember that this time for each and every waveform, or each and every case, each and every step, this time interval is fixed, as well as the height of the step is also fixed. That means the step size is also fixed. That means you, according to the input signal, you cannot increase the step size. The step size is fixed for delta modulation. Okay, so as it is comparing that this amplitude is greater than the previous amplitude, that's why upstep is produced. Again, this amplitude is the greater than the previous amplitude, again the upstep is produced. This amplitude is the greater than previous amplitude, again the upstep is produced. This amplitude is greater than previous, slightly greater than previous amplitude, again upstep is produced. Now this amplitude is less than this amplitude, that's why a downstep is produced. Now after this downstep, it is comparing this amplitude with this amplitude. It is saying that the current amplitude is greater than the last amplitude. Again, a upstep is produced. After producing upstate, after a particular time, it is watching this amplitude, the amplitude of the black signal or the input signal with the last sample amplitude. Again, a downstep is produced. After a downstep is after this downstep, after a particular time, it is waiting. It is holding this sample value for a particular time, and after a particular time, it is again saying that this amplitude is greater than this amplitude. This amplitude of the original signal at the particular time is greater than the last sample amplitude. Again, it is producing upstep. Now, as far as this constant valued signal will long last, there will be a continuous pulsating DM. That means the output of the delta modulation, the delta modulation output will be continuously pulsating for a continuous time signal, or almost constant signal. That means here a noise is produced. Though the input signal is not varying or the input signal is almost constant, the output of the delta modulation is continuously varying. This is called a noise. A noise is produced for a constant signal or almost constant signal. Okay, so this is called the granular noise. These are the two problems. What are the two problems? Again, I am going to repeat. The two problems are, if the signal is varying very fast or the initial slope or the slope of the signal at t is equal to 0 is very much high, then at that time the delta modulation cannot follow it, or the reverse is also possible. If the amplitude, if the signal slope is almost 0, means there is no slope, means signal is not varying too much or the signal is almost constant. For the constant value signal, there is a continuous pulses is producing for delta modulation. This is called the noise. Due to the fast varying signal, the slope overloads are produced. Okay, and due to the constant signals or the constant part of a signal, the granular noise are produced. These are the two major disadvantages of delta modulation. Now we will see how adaptive delta modulation has covered these disadvantages. See, for adaptive delta modulation or to cover these disadvantages, okay, we have to do two things. We can do two things actually. That is, if we, for delta modulation, whatever we have considered, the TS was constant and as well as the delta or the step size was constant. But to recover this, to recover DM problems, whatever we can do to recover DM problems, we can either vary the step size, we can either vary the sampling time, or we can also vary the step size. If we vary the sampling time, that means according to the input signal, first assume that we are varying the sampling time. Varying the sampling time means according to the input signal, the sampling time will be varied, but the step size will remain constant. Okay, the sampling time is varied means if it's noticed that the input signal is varying too much or the slope of the input signal is very high, at that time it will reduce the sampling time. Okay, but the step size will remain same. You can see that this time is not constant for each and every pulses. That is this time. It is the TS, not constant now. Okay, this TS is not constant now, but the step size are constant here. Using this technique, this is constant actually. Using this technique, or that means the only TS is varying, delta is constant. We can recover the problem, the DM problem, or we can do one thing. We can make TS constant. That means TS is constant, and we can vary the delta. We can make TS constant and we can vary the delta. At the time, what will happen? Let us see. Using this way, using both way, that means either you can vary TS or you can vary delta, you can recover this problem. At the time how the problems are recovering, you can see that here the TS is constant. That means this time interval is constant, but the step size, that the vertical step size are varying. That means this TS is suppose constant, but the vertical step sizes are varying. You can see that the TS, that is this TS is constant, but the step sizes, these step sizes or the vertical step sizes are varying. That means you can see the step size here is much more rather than the step size here. That means this step size is much more less than this step size, and this step size is another step, this is the another value, this is also the another value. That means according to the variation of the signal, it is just sometime it is just increasing its step size and sometime it is decreasing its step size. That means using both of these, okay, using both of these, you can remove the delta modulation problems. That means the slope overload as well as the granular noise, both can be removed. This for granular noise, how you can remove this? Suppose a constant value signal, if you consider the TS is varying and delta is constant, that means TS is varying, suppose the delta is constant, step size is constant, and you can do this. That means you can see that the step size, that is the delta, is constant, but the TS is varying. That means if we notice that there is a constant value at the forward step, at the present step, at the present state, that means at the present sample instances, if it locates that after these sample instances the signal is not changing too much, or the signal has the constant value, then it will increase, it will drastically increase it TS, or the sampling time interval, okay, so that the value after the sampling remains constant, or it can follow the input waveform. And for granular noise, in case of if the TS is constant and amplitude is varying, then what can happen? TS is constant means the horizontal portion, the TS, horizontal sampling time, is constant. Okay, horizontal sampling time is constant, but the amplitude or the step size, that is the delta, is varying over here. That means this is like this. you can see that this TS, this is the TS, is constant, but the step size, that is the step size, that is delta, vary. Okay, the TS is constant here, but the delta is varying. This is for slope overload, this is for slope overload, and this is for granular noise. One is for slope overload and one is for granular noise. Okay, for both slope overload and granular noise can be removed by either of these two ways. Okay, here the adaptive delta modulation comes into the picture. See, this process, that means varying TS, is not possible. Why varying TS is not possible? There is a basic concept of circuit that must come into your mind. That is, for sampling, we generally use a crystal oscillator. The crystal oscillator has a fixed frequency. Okay, that means fixed frequency means it has the fixed time period also. If the input signal is sometimes the input signal that we are feeding here, sometimes it may be a DC signal, or it may be a high frequency signal, or it may be a low frequency signal. For separate signal, it is not possible to change the crystal oscillator itself. It will be very much annoying and very much costly. Or it is not also possible that for defined frequency input signal, that means the input signal for the input signals of defined frequencies, defined transmitter has been designed. It is not possible also. Okay, that's why to vary the sampling time, it's not a smart work. Okay, sometimes the input may be like this, sometimes the input may be also like this. So if we design some separate circuits for these types of signal and these types of signals, and such like as for infinite number or infinite types of signal, if we have to design infinite types of transmitter, that is infinite types of delta modulation circuit, modulator circuit, it is not possible actually. That means that's why the varying of TS is not possible. That means if we want to vary TS, we have to design separate circuitries, or we have to change the crystal oscillator itself from the circuit. Okay, so that task is not too much smart task. So whatever we can do, that is the crystal oscillator, we are keeping that the crystal oscillator is fixed, that is the step size we can vary, but the TS, that the sampling time, is fixed over here. So this method is not applicable practically. Practically, this method is not applicable. Why not applicable? That I have already told you. The varying TS is not too much smart work, because to vary TS, there is a crystal oscillator in the circuit. Is the sampling and hold circuit, there is a crystal oscillator, or there is a IC. It is not possible for separate signal. We have to change the IC, so it is not possible to change the IC for different types of signal. Okay, so that's why this process is wrong process. So we can proceed with this process. Okay, that means we are keeping the crystal fixed. Crystal fixed means our TS, or the sampling time interval, that is fixed, but the delta or the step size is varied. And this is the delta modulation, adaptive delta modulation. That means adaptive delta modulation is what? Here the TS is actually the constant, that the sampling time interval, that is constant, but the delta or the step size is varying. Okay, the TS is constant, but the delta is varying. The step size is varying. How the step size is varying? The step size is varying according to the input waveform variation. Okay, it is very easy. Just look at this, you will understand easily. See, I have taken such types of signal where a granular noise can be present. If we do the delta modulation of this signal, you know that for constant signal a granular noise can be present, and for a drastically change signal there must be present a slope overload problem in case of delta modulation. But let us see what the adaptive delta modulation handle these types of input signal, how it can handle it. See, the TS or the time interval is fixed. Okay, the time interval is fixed. These are the time intervals that is fixed. This is TS. This is fixed. So what it is doing actually, it is the varying the step size. Suppose at this time it is seeing that it is starting from this time actually. Let us see. At second sampling, at the second sampling time, suppose at t equal to 1, it is watching this, the amplitude of the signal has been varied too much. At that time it will increase its step size. This is the step size. It will increase its step size. If it locates after this, it is seeing, suppose the amplitude is not varied too much, at the time it will decrease its step size. Okay, again at this instant it is seeing that the amplitude is not varied too much, so it has decreased its step size. And here again it is seeing the amplitude has been varied too much, again it is increasing step size. Again it is seeing the amplitude has been varied too much, again it is seeing the amplitude has not varied too much. That means the difference of this sample and this sample is not too much, so the step size is reduced. Again here it is seeing the amplitude has been varied a little more, it will increase the step size. Here this will happen, and here after this it is seeing that the amplitude has been varied a little more. That means the present sample amplitude is little more. The difference of the past sample amplitude and the present sample amplitude is very small, so it will increase step size but very small. Again here it is seeing the amplitude is small, here like this, here like this, until like this. So you can see that the sampling time instances is fixed, but the step size is varying. I am assumed here two step size, that is, this is the delta 1, this is delta 2. Here you can see that the delta 1 is not equal to delta 2 actually. Okay, that means that in case of adaptive delta modulation, the sampling time interval is fixed and the step size is varied according to the given input signal. If the input signal variation is very large, if the input signal variation is very large, then large step size will be used. That means the system will automatically increase its step size, and the input signal variation is very small, something like this, then the small step size will be produced by the system itself. We don't have to do external things, or we don't have to provide some external circuitry or external control to vary the step size. The system will automatically do it, so no need to worry about it. Okay, so that's why for adaptive delta modulation, whenever we will see the block diagram, we will see a new thing, that is the step size control. There will be such block which will control the step size. Okay, so this is the ADM of the adaptive delta modulation. Okay, and how the granular noise and the slope overload has been reduced just by varying these. So for adaptive delta modulation, this thing is very much important. That is the varying step size. Now let us talk about the sigma delta modulation. For sigma delta modulation, this is same as a delta modulation. The technique of the sigma delta modulation is same. That is the name itself suggests, that is the SDM, sigma delta modulation. The name itself suggests that it is a delta modulation. But as there is a sigma block over there, that's why it has told that it is a sigma delta modulation. If the sigma blocks are 2 in number, see, if you find that in the circuit there are 2 sigma blocks, then it will be told as a second order sigma delta modulation. And if you find that there is a single block of sigma, there is a single sigma block, then it will be told as first order sigma delta modulation. See, the sigma block is nothing but a summation block. I will show you the laboratory tenor kit diagram or the block diagram. Okay, you don't need to worry about it. So just for sigma delta modulation, I am not going to details as this is not provided in our theoretical syllabus. So for sigma delta modulation, you have to notice in the circuit, if you find that there are 2 sigma blocks, then it will be the second order sigma delta modulation. There is a single sigma block, at that time there will be a first order sigma delta modulation. Now the last thing that we will study over here, that is demodulation. Okay, demodulation. See, after DM or ADM, for ADM also the rest of the thing is same. That means whenever the upstep is produced, suppose at this time this is 1, whenever the upstep is produced, it will produce a 1. Okay, that means the digital data, the processing or the producing of the digital data for DM and ADM is same. Whenever a upstep is produced, 1 is produced. Whenever a downstep is produced, and 0 is produced. Okay, the difference is the production of these 1s and 0s is considered upon the variation of the input signal. In case of delta modulation, that is for this, for delta modulation, as the step size and the TS was constant, it was checking the input signal, but it was not checking the variation of the input signal. That means the system parameters, that means these are the 2 system parameters, was not being varied according to the variation of the signal, because it was not checking the variation actually. Okay, but for adaptive delta modulation, we will vary the system parameters, that is the TS as well as the step size, according to the variation of the signal. That's why the code that will produce, that the adaptive delta modulation will produce, if we demodulate this code, you will find more appropriate input signals. The input signal that you will find here is near, it will be the more accurate. Okay, the error will be very much lesser than that of the delta modulation. Okay, now the demodulation techniques. Suppose now we have seen that the sigma delta modulation or adaptive delta modulation, it will produce some bit streams. Suppose, let us take an example. For an example, I am taking that these bit streams has been produced by a DM. This might be produced by a DM also, by ADM also, whatever, by sigma delta modulation also HDM, whatever a B stream is produced, suppose I have taken. Now according to the B stream, first of all what it will do, there is a step size controller, not the step size controller actually, there is a circuitry that will produce the steps. That means sometimes it will produce the up step, sometimes it will produce the down step. So for 1, up step will be produced, for 0, down step will be produced, and for 1 up step will be produced, up step will be produced in number of 1 and down step will also produced in number of 1. So first I will see that there is a 1, so 1 up step has been produced, again a 1, again 1 up step has been produced, again a 1 up step produced, then there are 3, 3, 6, 7 zeros, so 7 down step will be produced, 4, 5, 6, 7, then again 2 up steps will be produced, 1, 2. Okay, this is the corresponding signal that will be produced by the demodulator circuit. Now this is not also complete, it has just produced this, it has just represent this the codes or these digital signals in the form of analogous or is the sampled form. Now there will be an integrator. What the integrator will do, this step is very very important. For integrator, I am taking a signal. Suppose this is a pulse, and amplitude of this pulse is A, and this pulse has presence A to T. If we integrate this from 0 to T, as the pulse is present from 0 to T, okay, that's why we are integrating from 0 to T. Actually the integration is done from minus infinity to plus infinity. Now minus infinity to 0, this signal is, actually I'm right, actually they like this, minus infinity to plus infinity, I am integrating this AT signal. Now as from minus infinity to 0 and then from 0 to T, I am just dividing this integral into 3 parts, then T to infinity, I have just divided the integral limits into 3 parts. Now from minus infinity to 0, the signal has no value, so that's why this value will be 0. From T to infinity, this signal don't have also any value, that's why this value will be 0. Now from 0 to T, this signal has a value and that is A, so integration 0 to T A dt. So A dt means A is constant, actually integration 0 to T dt. Okay, and that is nothing but T integration 0 to T. Now AT, from 0 to T AT, this is nothing but a ramp signal. That's why from 0 to T a ramp will produce whose slope, okay, whose slope will be A. Okay, a ramp is produced, the slope will be A. If the AT is produced, that means here A is the slope. If 2T will be produced, then the slope will be 2, something like this. From 0 to 2 a ramp will be produced. Using this concept, we can also tell that the from pulse signal, if we provide an integrator, it will produce a ramp. The vice versa is also true. If I take a ramp signal, if I provide it into the differentiator, a pulse will be produced. How this is possible, I am also showing this. Suppose a ramp signal 2t has been taken. Suppose xt is equal to 2t. If we differentiate ddt of xt, then what is produced here? 2 of ddt of t, that is nothing but 2. What is 2 actually? The signal 2 can be represented as a DC value. This is 2. That means we are providing a 2t, that is the ramp signal. Okay, 2t is nothing but a ramp signal. Okay, where the slope is 2. We are providing the 2t. Okay, and if we differentiate this 2t, the ramp signal, a step signal is produced. For step, if we integrate a step signal, the ramp will be produced. If we integrate a if we differentiate a ramp signal, a step signal will be produced. And using this concept, after producing this sampled signal from this code, there will be an integrator. Okay, integrator. And what the integrator will do? Integrator will just integrate these total signals. See, for this, as you can assume that there are number of steps here. Actually, right? The signal consists a number of steps. Actually, so for each and every step, it will perform the integration. For this step, it will integrate like this. For this step, this will integrate like this. For this step, like this. For this step, like this. And again for this step, like this. For this step, like this. As the step is downwards, then the also slope will be downwards also. Like this, and something like this. After that, and it will again increase. So you can see a triangular waveform is producing. Okay, for DM, ADM, whatever, a triangular waveform will be produced by the demodulator circuit. That means a demodulator, what will do? Demodulator first convert this bit stream into a corresponding sampled signal, or just looks like a PAM signal, and after that it will just integrate this signal. Okay, after integration it will find triangular signal which is very much closer to a sinusoidal signal. Okay, you can see that this is almost sinusoidal, but not the particular sinusoidal, because the sinusoidal signal will looks like this. It was like this, and it is almost sinusoidal. That means we have detected the input signal that we had provided. Okay, and now I am going to show our theory portion is actually completed. Okay, now I am going to show you the circuit diagram as well. So this is the first circuit diagram. Just look at this right now. This circuit, like this. Okay, this circuit, this circuit is the DM circuit. This is for DM, and this is for ADM, and this is the sigma first order. Okay, sigma first order. This is DM, this is ADM, and this is sigma first order. Okay, so look at DM first. At DM, whatever I have told, that is the delta modulation. The input signal will be sampled by a sample and hold circuit that I have already shown you. And after the sample and hold circuit, according to the sample and hold circuit, the codes will be generated, and this signal, you can have understood this signal right now. Okay, because this signal is nothing but the signal that has the constant TS, that the constant sample time, and as well as the constant step size. This is actually the DM signal. And DM output signal in the form of this pulse means actually DM output is nothing but in the form of codes, like these types of codes, these types of codes. So this, if we represent these types of codes, then what will happen? This will like 1, again this is, there will be 1, then 1 1, then it will be 0 0 0 0, again 1 1, you know, just like this. So that's why a symbol has been shown here. This is the digital signal, that is the digital bit streams. Okay, and there is a feedback loop. Okay, so this is the DM actually. Now there is a small mistake in this diagram. Actually the DM is this. Okay, this is the DM actually. DM waveform is this. Okay, now this is the actually ADM. Why this is ADM? I have already told you that the DM had two more disadvantages. Two major disadvantages was one was slope overload and another one was granular noise. And to remove these disadvantages, we must have to vary either TS, that means the sampling time, or the step size. Okay, so the sampling time variation is not too much practical. That means we don't want to change our crystal oscillator again and again for different kinds of input signal, but whatever we can do, we can vary the step size. And for varying the step size, I have also shown you. That means let me check it. Yes, for vary the step size, I have already told you there is step size controller that I have already shown you. Step size controller is required. That means the DM and ADM block diagram is almost same. There is certain circuitry for controlling the step size. That is like this. You can see that there is a step register, and this block has been introduced in ADM. The rest of the circuit is almost same, and it is like nothing like but feedback. Okay, so rest of the circuitry is same. And one more thing, step register, after the step register there is a accumulator, that is add or subtract. What is the meaning of add or subtract? Actually the add or subtract is nothing but what is actually doing, there is a fixed step size. Okay, suppose the step size is suppose delta. Okay, delta is a fixed step size. Whenever we need to increase the step size, then it is just adding a value to delta. Whenever we need to decrease the step size, it is subtracting a particular step from delta. So that's why it is sometimes adding a step and it is sometimes subtract a step. And this delta 1 has been stored in this step register. Suppose the delta 1 has been stored in this register. A fixed step size is already there in accumulator. Sometime addition or subtraction has been performed with this fixed step, and in between the fixed step and this delta 1. So addition is for increasing the step size and subtraction is for decreasing the step size. So that's why accumulator or the adder or subtractor has been provided, just to increase or decrease the step size according to the input signal variation. Okay, very much easy. And this is the DM that I have already told. Okay, this is the sigma delta modulation of first order. So there is nothing to be understand. The input circuit is same, that is the sample and hold circuit here. There is a summation block, and this is the sigma. This is the first order, one sigma block. One sigma block means this is the first order. In second order circuit, that means in trainer kit, that circuit diagram I am also going to show you. That means in trainer kit, you will also see that there is a second order sigma delta modulation, and in that circuit you will find there are two sigma blocks. Okay. There is nothing to understand about this blocking or about this circuit diagram of the sigma delta modulation, because yes, this is not in our syllabus. I am not bothered. We are not bothered about how the circuit is performing, how the circuit is operating actually. Okay, so no need to worry about it. See, this the circuit diagram that now I am going to show you. This is the trainer kit circuit diagram actually. This is the original trainer kit circuit diagram. Listen to me carefully, whatever you have to do in case of laboratory. See, there is a signal type. There is a signal type. This. There are several types of signal, that is sine, square, triangular, arbitrary signals also are there. Signal types mean the input signal that you are going to provide, that may be sinusoidal. Whatever calculation I have done in theory, that is I have shown that we are sampling a sinusoid, right? That means we are giving input as the sinusoidal signal. So for sinusoidal signal, you must have to choose the sine. Generally, we don't need to worry about the selection of the type of the signal. That the selection of the type of the signal will remain in sine for always. Okay. But for knowledge, we are telling that we are considering that there are also several options for selection of several types of input signals. This is the signal frequency. The signal frequency means this frequency is for this input signal. For sinusoidal signal, that means here sinusoid has been selected. So we are giving input a sinusoidal signal of frequency 500 Hz. You can see that the block of 500 Hz block LED is glowing. That means we have selected a sinusoidal signal of frequency 500 Hz. This push button, using this push button, we can select or deselect the frequency range, as well as using this push button we can also select these types of the signals. Okay. Now this is the signal generator. Whatever data, whatever the signals, whatever the types of signal that we have selected, whatever the frequency we have selected, according to these parameters, this signal generator will generate a signal, and this signal is feeding this. See, this upper block is the delta modulator that I have already shown you in our previous diagram. This upper block is delta modulator. This is adaptive delta modulator. This is sigma delta first order modulator. This is sigma delta second order modulator. Okay. Now I have already told you that for sigma delta first order modulator you will find a single sigma block, but for sigma delta second order modulator you can see here that I have already told you there are two sigma blocks. Two sigma block means sigma delta. This is the second order sigma delta modulation. Okay. Now using this switch, there is a switch, that is the modulation technique selection. Whatever modulation you have to do, you can perform 4 types of modulation in this trainer kit. Using this switch, momentarily you can select these 4 types of modulation. You can switch these 4 types of modulation. Okay. That means whenever delta modulation is required, you need to perform the delta modulation. Just by pushing this switch, you have to select the delta modulation block. Now you can see the it is the sigma delta first order modulation has been selected, because the input and output LED of sigma delta first order modulation is glowing, means the sigma delta first order modulator has been selected here. Okay. And this block is for sampling frequency. See, at sample and hold circuit, at the point number 3 here, point number 20 here, point number 29, point number 37, here we are actually feeding the sampling frequencies. Okay, the sampling signals. That means we are feeding actually we are feeding a pulses. Okay, actually the impulse sampling is ideal sampling, but I have already told you at the starting of today's video or at the last video that impulse sampling is not practical. That's why we use the pulses or small widths. Okay, so Small width means the sampling frequency is much higher. And how much higher? That means sampling frequency must be at least twice of the, greater than twice of the input signal frequency. That is the Nyquist criteria. That means that we have just selected the lower sampling frequency, that is the 16 kilohertz, and by pushing this button you can switch between the several sampling frequencies. By default the 16 kilohertz has been selected, which is more than enough. Okay, and from here, see, now the vital step is coming. At the input of the sample and hold circuit, you will find the signal that is provided. The input sinusoidal signal is fed here, and the signal of the input sinusoidal signal is looks like this. I hope that you can see the input sinusoidal signal in the screen, because this signal has been captured, this picture has been captured from the DSO in the laboratory. This is the signal that is the sinusoidal in nature, and as well as the 500 Hz frequency, that is clear, that can be clearly calculated using the time divisions as well, the basic calculation actually. So you can see the sinusoidal signal as well as the 500 Hz frequency has been fed to all of the inputs of the sample and hold circuit. Okay, and at the sample and hold circuit we are also feeding this signal. It is nothing but the clock signal, that is the sampling frequency of the 16 kilohertz. If you calculate the time using the time division, you will find that it is near about the 16 kilohertz. Actually it is not possible to exactly produce the 16 kilohertz frequency, because the crystal has some limitations also. Okay, so if you calculate using time division, you can see that this is the 16 kilohertz, and this is also obviously the square wave that I have already told you. Okay, that is the pulses actually. Impulses is not possible to produce. Okay, this is the pulses. And after the sample and hold circuit, the sampled sinusoidal signal is being produced. You can see this signal, there are several steps, like the sampled sinusoidal signals has been produced. It is the same sinusoidal signal, but due to the sample and hold circuit, the sampling and holding has been done over here. Okay, sampling and holding has been done over here, and these three are same for all of the four types of delta modulation. Okay, and at output of delta modulation, adaptive delta modulation, you will find several digital pulses. These digital pulses signifies actually the values of the output, whether it is 0 and 1. If it is 0, then a negative pulse has been produced. If it is 1, then a positive pulse has been produced. Okay, now the output of the delta modulation I have already shown you, that is actually the triangular waveform, right? For adaptive delta modulation as well as the delta modulation, this is the triangular waveform. I am showing the output. Okay, and one more thing, you can see here that there is an integrator that I have already told you. See, there is a integrator. Why the integrator? Because from that signal, that the form this digitized, the digital output signal, it is was producing the sampled sinusoidal signal, and from the sampled sinusoidal signal, if we integrate each and every pulses, you will find a ramp. That means a perfect triangular signal will be produced. See, and perfect triangular signal will be produced theoretically, but there will be much more distortion. I am showing the signal that was produced in the laboratory during experiment. Now this is the signal. I hope you can see it over the screen. This is the signal that has been produced during performing the laboratory experiment. This is the triangular signal, but little more distorted also. And this signal Now this signal is for the adaptive delta modulation. This signal is same input signal that was provided in the delta modulation. This is the same clock pulse, and this is the same sampled sinusoidal signal. Okay, the same sampled sinusoidal signal, because I have already told you these three signals, that is input signal, sampled signal, and sampling clock signal, is same for all of these. And this is the digital output of the ADM, that is the adaptive delta modulation, and this is the triangular output. I know this is not triangular. You might ask me a question. It is much more distorted, but if you calculate the frequency of this signal, okay, if you calculate the frequency of this triangular signal, obviously, if you calculate the frequency of this triangular signal, you will find a closer value to a 500 Hz. Why? Because the input signal was of 500 Hz. So obviously the demodulated signal that we will get must have to be of 500 Hz, right? So it is also a triangular signal, a little more distorted. Okay, not little more, it is much more distorted, whatever. Now sigma delta first order and sigma delta second order, I have not performed sigma delta second order because as sigma modulation is out of syllabus, so that's why you have just performed a basic thing, that is sigma first order modulation only. And for sigma first order modulation, the output will not be the triangular form. You just have to remember it. Why not? This is not required too much. Okay, because for sigma first order modulation, we are not using integrator, actually we are using decimeter. Okay, so now it is not too much required to know the working of the decimeter, but just to remember that for sigma modulation, the triangular waveform will not be produced. The waveform that is seen over here, that is the first three waveforms that I have already told you. This is the third time I am telling. The input signal, sampling clock, okay, the clock for sampling whole circuit, and as well as the sample output signal will be same for all of the three experiments. That is the input signal, this is the sampled signal, sorry, this is the sampling clock signal, and this is the sampled signal. Okay, and one more thing that you have to understood, that for adaptive delta modulation, if you see clearly the sampled signal, you will find that the step size is varying here. The step size is much more at the middle, at the x-axis line, and it has been reduced at the peaks point. That means at the valleys of the input signal, the step size is more, and at the peak of the input signals, that the positive peak and the negative peak, the step size has been reduced, because that in peaks the variation is not too much, right? So that's why the step size has been reduced. It is for adaptive delta modulation only. Okay, and the output of the sigma delta modulation will be like this. I have already told you, that is the triangular waveform will not be produced here. Okay, so this as the indicator is not used here, and decimeter is used here, that's why the output will not be in the triangular form. Okay, so hope you have understood this. If you have any query, you can ask me doubts, and I will provide these notes in the comment section. You can check it out. Okay, that's all for today. Hope all of you have enjoyed, and if you have really enjoyed, you can smash the like button. Okay, and for you may also subscribe my channel, so that whenever I will upload a new video, you will begin notified soon. That's all for today. Bye bye. See you in the next video. Until then, thanks for watching.